What if a black hole entered our solar system? Not a supermassive black hole from the center of a galaxy. Not a mysterious object large enough to swallow the sun from thousands of astronomical units away. Imagine something much more ordinary by black hole standards, and therefore more interesting. A lone stellar mass black hole, 10 times the mass of our sun. No companion star, no bright accretion disk, no glowing beacon announcing its presence. Just about 10 solar masses compressed behind an event horizon roughly 30 kilometers across, moving through the galaxy at about 50 kilometers per second. And one day, by an accident of geometry and extraordinary good luck, astronomers discover that it is heading directly through the outer solar system. Its predicted closest approach to the sun is not inside the sun, not near Earth. 5 astronomical units. Roughly the present distance of Jupiter from the sun. That sounds reassuring until you remember one number. The black hole has 10 times the sun's mass. Tonight, let your body settle into wherever you're resting. And let's follow this impossible to ignore visitor from the moment humanity first notices that something dark is moving toward us. The story begins not with darkness, but with a star becoming slightly brighter. At an observatory in Chile, an automated survey flags an unusual event in a crowded patch of sky. A background star has brightened. That by itself is not remarkable. Stars vary. Instruments glitch. Objects pass in front of one another. Astronomical databases contain millions of events that become less mysterious once enough data arrive. But this star has not changed in the usual way. Its light curve has the smooth symmetry of gravitational microlensing. Something massive has passed almost directly between Earth and the distant star. The invisible foreground object's gravity has bent the background starlight, briefly magnifying it. The software sends the event to a team for follow-up. One of the people who opens the alert is Dr. Elena Vasquez, 34 years old, an astronomer who studies astrometry, the exquisitely precise measurement of positions on the sky. She expects a normal microlensing candidate, a faint star, a brown dwarf, perhaps, if the data are unusually exciting, a compact remnant. Instead, the position of the background star appears to shift by far more than expected. Elena checks the calibration. Then she checks it again. A second observatory confirms the displacement. The background star is not physically moving that way. Its apparent position is being bent by gravity. The lens must be close. Very close by astronomical standards. Elena's first thought is that the mass estimate must be wrong. Her second is that the distance estimate must be wrong. Her third is not something she says aloud. If both are right, this thing is inside the solar system. Within 24 hours, telescopes around the world are looking at the same patch of sky. There is no visible object at the predicted position. Infrared observations find no ordinary star bright enough to account for the lensing. X-ray telescopes see no luminous binary system. Radio observations find nothing obvious. But the lensing continues. And as Earth moves around the sun, the apparent geometry changes enough to reveal an enormous parallax. The invisible lens is not thousands of light years away. It is hundreds of astronomical units away. The first public estimate places it around 600 AU from the sun. That is 600 times the average Earth-Sun distance. Far beyond Neptune. Far beyond the main Kuiper belt. Close compared with interstellar space. Elena's team spends a sleepless week combining the lensing data with decades of precision observations of the outer planets. Something else is there. The orbit of Neptune shows a minute discrepancy. So do the trajectories of several distant trans-Neptunian objects. Each discrepancy is tiny. Together they point toward the same region of sky. The invisible object's gravity is already pulling on the solar system. Not dramatically, not enough for anyone to feel, but enough for mathematics to notice. The mass estimate tightens. 8 solar masses, then 11, then 10.4, with uncertainty. The scientific community stops using the phrase compact object candidate. The object is too massive to be a white dwarf. It is dark. It is isolated. And the best explanation is a black hole. For the first time in human history, a confirmed stellar mass black hole is not thousands of light years away. It is in the sun's extended neighborhood. Then orbital dynamicists calculate the trajectory. That is the moment the discovery changes from extraordinary astronomy into a planetary emergency. The black hole is not bound to the sun. It is passing through. Its speed far from the sun is around 50 kilometers per second. At its current distance, a simple distance divided by speed estimate gives a little under 57 years before it reaches the inner planetary system. Gravity will accelerate it as it falls toward the sun, so the last part of the journey will happen faster than that simple estimate suggests. And the best fit trajectory passes about 5 AU from the sun. Elena looks at the simulation on her screen. A black dot crosses a diagram of the solar system. The dot is almost comically small. The gravitational influence is not. She watches the projected path pass through the region occupied by the giant planets. One colleague says, very quietly, "That can't be right." Another answers, "It is." By the following morning, governments have been informed. By the following evening, the world knows. The first headlines use the word monster. The second wave uses killer. Videos appear showing a black sphere vacuuming planets into a giant mouth. Those videos are almost entirely wrong. And that matters, because the real danger is more subtle and, at planetary scale, more profound. A black hole is not a cosmic vacuum cleaner. Outside its immediate vicinity, gravity does not care that the mass is hidden behind an event horizon. If the sun could somehow be replaced by a black hole with exactly one solar mass, Earth would continue orbiting almost exactly as before. We would freeze because sunlight disappeared, but we would not suddenly spiral into the black hole simply because the sun had become dark. At a distance of 1 astronomical unit, one solar mass produces the same gravitational field whether that mass is a star, a black hole, or an impossible compact ball of ordinary matter. Our visitor is dangerous because it contains 10 solar masses. If a 10 solar mass star passed 5 AU from the sun, the gravitational problem would be nearly the same. The word black hole adds exotic physics near the event horizon. The mass creates the solar system catastrophe. This becomes the first lesson astronomers repeat until everyone is tired of hearing it. The event horizon of a non-rotating 10 solar mass black hole is only about 30 kilometers in radius. 30 kilometers. The entire object that frightens a planet could hide inside the distance many people commute to work. Earth is not going to be swallowed from millions of kilometers away. The black hole does not send out a suction force. It does not reach across space with anything stronger than gravity. But 10 solar masses moving through a planetary system is enough. The next question the public asks is obvious. Can we stop it? The answer arrives almost immediately. No, not with any technology remotely available. Humanity has learned to change the paths of small asteroids by tiny amounts. We can imagine pushing larger asteroids if given enough time. We can send spacecraft into comets. We can use gravity assist from planets. A 10 solar mass black hole is different by absurd orders of magnitude. Its mass is about 20 billion trillion kilograms. There is no surface to strike. No engine we could build could appreciably change its velocity. No nuclear arsenal matters. Even if every weapon humanity possesses could somehow deposit its energy with perfect efficiency, the resulting change in the motion of 10 solar masses would be essentially irrelevant. And there is another uncomfortable detail. This black hole does not need to hit anything. A miss by billions of kilometers can still reorganize the solar system. The immediate fear therefore changes. Humanity is not planning to destroy the intruder. Humanity is trying to understand what the intruder will do. The first simulations disagree badly, not because physicists do not understand gravity, because planetary systems are complicated. The exact effect depends on the black hole's mass, speed, direction, and closest approach. It depends on where Jupiter is in its orbit when the black hole arrives, where Saturn is, where Earth is. The angle between the intruder's trajectory and the planetary plane matters. Small changes in the predicted path, multiplied over 50 years, can alter which planet receives the strongest encounter. So the first global response is not construction. It is measurement. Every suitable telescope is recruited. Astrometric observations refine the black hole's position. Microlensing events occur as it sweeps across the background star field, providing more mass information when the geometry is favorable. Planetary ranging data are reanalyzed. Spacecraft radio tracking becomes part of the solution. Astronomers search old photographic plates and archived survey images for earlier lensing signatures. The object itself remains almost perfectly dark. Humanity learns its path by watching everything around it move. Elena becomes one of the public faces of the discovery because she is unusually good at explaining this. In an interview, a presenter asks what the black hole looks like. Elena says, "Mostly, it looks like other things being slightly in the wrong place." The sentence becomes famous. It captures the strangeness. For a star, astronomers collect light. For this object, they collect absences and distortions. A star brightens because space-time bends its light. Neptune arrives a little early relative to one model and a little late relative to another. A distant icy body drifts from the orbit it should have followed. The black hole announces itself by changing relationships. For the first few years, nothing changes in ordinary life. The sun rises. The moon moves through its phases. Jupiter is still a bright point in the night sky. The black hole is still hundreds of AU away. At 600 AU, it pulls strongly on the solar system as a whole compared with an ordinary distant star, but much of that acceleration is shared. The sun moves toward it. Earth moves toward it. Jupiter moves toward it. If every part of the solar system experienced exactly the same acceleration, the internal planetary orbits would barely notice. What matters is the difference in gravitational pull from one location to another. Tides. Not ocean tides yet. Gravitational tides in the general sense. The black hole pulls a little more strongly on the side of the solar system nearer to it, and a little less strongly on the far side. Across Earth's 1 AU orbit, at a black hole distance of hundreds of AU, that difference is still small. Across Neptune's 30 AU orbit, it is much larger. This is why the outer solar system becomes the first place where the visitor leaves fingerprints. At roughly 1,000 AU, the tidal acceleration across Neptune's orbit from a 10 solar mass intruder is on the order of a few 10,000ths of the Sun's own gravitational acceleration at Neptune. At 600 AU, the ratio rises to around a few tenths of 1% in a favorable geometry. That is not enough to tear Neptune away immediately. It is far more than enough to matter to precision orbital measurements. And farther out, where comets orbit only weakly under the Sun's control, the disruption is much larger. Long before the black hole threatens the known planets, it moves through the architecture of the Oort cloud. The Oort cloud is not a bright shell we can photograph. It is a hypothesized vast population of icy bodies extending thousands to perhaps tens of thousands of AU from the Sun. Those objects are only weakly bound. Passing stars can disturb them. The galaxy itself can disturb them. A 10 solar mass black hole passing through that region is an extreme gravitational visitor. Some comets are nudged into tighter solar orbits. Some are pushed outward. Some are ejected from the solar system entirely. Some become bound to the black hole for a time. But there is no immediate reign of comets on Earth. Orbital mechanics has a sense of delay. An object thousands of AU away can be redirected today and require centuries or millennia to reach the inner solar system. So the first legacy of the black hole may arrive long after the black hole itself has left. Astronomers begin talking about a future comet shower that nobody alive at Discovery may ever see. That is strange enough. Then the object reaches 500 AU. The countdown has become a generation. Children entering school will be middle-aged when the black hole crosses the giant planets. People begin making decisions with the encounter date in mind. Governments create permanent planetary dynamics agencies. Insurance contracts acquire clauses no one had imagined. Universities build entire programs around encounter science. Religious movements appear. Conspiracy theories flourish. Some people insist the trajectory has been invented to justify global spending. Others claim the black hole is an artificial object. A few say calculations are meaningless because 50 years is too far away to predict anything accurately. In one sense, that last complaint contains a serious point. The path can be predicted extremely well if the mass and current velocity are known, but the outcome for individual planets remains sensitive to geometry. So astronomers keep measuring. The predicted solar closest approach settles near 5.1 AU. The uncertainty shrinks. Jupiter will not be exactly at the closest point. That is good. Saturn will be farther away. That is also good. But the black hole will pass close enough that the Sun itself cannot be treated as a fixed center anymore. The solar system is about to meet an object 10 times more massive than its star. The phrase black hole enters the solar system begins to sound too mild. The center of gravity is coming to us, and there are still 50 years to wait. Those 50 years transform science into infrastructure. The first major project is called simply the Encounter Atlas. It is not one simulation. It is billions. Supercomputers run slightly different versions of the future, varying the black hole's position by kilometers, its velocity by millimeters per second, the masses of planets within observational uncertainty, the locations of asteroids, and the timing of the encounter. Most large-scale results agree. The black hole will pass through the giant planet region. The Sun will be strongly deflected. The outer planets will be severely disturbed. The solar system after the encounter will not have the architecture it has now. The inner planets may survive. That word, may, becomes the center of civilization's anxiety. Earth's fate is sensitive to details. The black hole does not need to come close enough to produce dangerous tidal forces across Earth's body. It can threaten Earth by changing Earth's orbit around the Sun. This is the second great lesson of the event. A planet is habitable not only because its surface is safe. It is habitable because its trajectory is safe. Earth moves around the Sun at roughly 30 kilometers per second. That motion is not an optional background fact. It is why we do not fall into the Sun change Earth's orbital velocity by enough, or change the Sun's velocity relative to Earth, and the orbit changes. Make it more eccentric and seasons become more extreme. Increase the orbital energy enough, and Earth can escape the Sun. Decrease it enough, and Earth's orbit can move inward. A passing massive object can do all of these depending on geometry. The public keeps asking for one answer. Will Earth survive? Dynamicists keep answering with probability distributions. That frustrates everyone, but it is honest. At 48 years before closest approach, the best models give several broad classes of outcome. In many, Uranus and Neptune are displaced dramatically or ejected from the solar system. In some, Saturn is lost. Jupiter survives more often, but may emerge on a radically different orbit. The inner planets are better protected because they are more tightly bound to the Sun and because the black hole does not pass among them. Yet, even Earth can receive a substantial gravitational kick relative to the Sun because the black hole's pull is not identical at the two positions. No serious model predicts that everything simply continues normally afterward. Humanity begins preparing for uncertainty rather than one apocalypse. This matters. If Earth is ejected from the solar system, Long-term survival on the surface becomes nearly impossible without an enormous artificial energy infrastructure. If Earth remains bound but moves outward, cooling may be the major problem. If the orbit becomes strongly eccentric, agriculture and climate stability may be devastated even though sunlight never disappears entirely. If Earth moves inward, heat becomes the crisis. If Earth's orbit changes only moderately, civilization may survive a terrible century and recover. The same black hole flyby can create all of these in neighboring simulations. So governments do something unusual. They prepare for several planets at once. Food systems are redesigned to tolerate sunlight changes. Seed banks expand. Artificial light agriculture scales up. Nuclear power, geothermal power, and long-duration energy storage become strategic projects not because the sun is expected to go out, but because nobody can guarantee how much solar energy a future Earth will receive. Coastal infrastructure is reconsidered, not because the black hole will raise one giant ocean tide from 5 AU away. It will not. At those distances, direct tides across Earth are small compared with the forces that could tear the planet apart. But if Earth's orbit changes, climate changes. If the moon's orbit changes, tides change. If large asteroids are disturbed, impact risk changes. If society loses satellites during orbital chaos, communications and weather forecasting change. Preparation becomes less cinematic than the headlines predicted. Warehouses, power grids, greenhouses, water systems, archives, hospitals, training. Nothing looks like a weapon aimed at the black hole because there is no useful weapon to aim. The most ambitious project is not planetary defense. It is planetary insurance. At 45 years before encounter, Elena visits a school. A boy raises his hand. "Why don't we move Earth?" The room laughs. Elena does not. "That is actually the right kind of question," she says. Then she explains the scale. Moving Earth even slightly requires changing the momentum of a planet with a mass of almost 6 trillion kilograms. Humanity can move spacecraft. We can change asteroid orbits by tiny amounts. Over enormous timescales, hypothetical schemes involving repeated gravity assists from asteroids or giant engineering projects could alter planetary orbits. 45 years is not enormous. The black hole is. "So we can't do anything?" the boy asks. "We can do a lot," Elena says. "We just can't do everything." That sentence becomes another one people remember. Civilization has spent centuries equating capability with control. The black hole offers a different lesson. Understanding a danger does not imply being able to remove it. The same year, the first dedicated spacecraft launches toward the incoming object. Not to stop it, to measure it. The probe is designed to pass through the region ahead of the black hole and observe whatever faint emission may exist from material falling toward it. An isolated black hole is not necessarily perfectly silent. As it moves through interstellar gas and later through the solar wind, some particles can be gravitationally focused and accreted. If enough matter falls inward and heats, it can produce radiation. How bright this would be depends on the density of surrounding gas, the black hole's speed, magnetic fields, and the efficiency of accretion. Astronomers do not promise a glowing disk. There may be none. At 50 kilometers per second, the object moves quickly through thin gas. But as it enters denser regions of the solar wind, instruments may see X-rays or radio emission associated with accreting plasma. This is useful scientifically and emotionally. For years, humanity has known the black hole mainly from what it does to other objects. Now there is a chance it may begin to glow faintly. The first detection comes 37 years before closest approach. It is weak, a small excess in X-rays, then radio emission. Models disagree about the exact source. After months of confirmation, astronomers conclude that at least some of the signal is associated with gas being captured by the black hole. The public response is immediate. For the first time, there is an image. Not an image of the event horizon. The black hole is far too small on the sky. The picture is a faint, unresolved point produced by hot material around an invisible mass. Still, people look at it for hours. A thing that had existed only as equations has become a pixel. Elena is 54 by then. Her hair has gone gray. She keeps the first image on the wall of her office. Visitors are disappointed by how unimpressive it looks. That's it. But it doesn't look like a black hole. It looks like matter having a bad day near one. The line circulates online. By this stage, the visitor is around 400 AU away. The giant planets are no longer merely showing tiny residuals. Their orbital solutions visibly require the black hole. Navigation teams for outer system spacecraft update trajectories constantly. Some probes that were intended for long scientific missions are repurposed as gravitational test masses. Every radio pulse sent to them adds another constraint to the intruder's field. The black hole becomes the best measured invisible object in history. Then humanity receives the first reminder that the solar system extends far beyond planets. A long-period comet appears. That is not unusual. Then another. Then a third with an orbit that traces back toward the region through which the black hole has moved. The temptation is to announce the predicted comet storm. Dynamicist refuse. The timing is too soon for many distant Oort cloud bodies perturbed during the current passage to have reached the inner system. Some of the observed comets may have been altered earlier in the black hole's approach, when it was still thousands of AU away. Some may be unrelated. The statistics take years. Eventually, a pattern emerges. The incoming black hole has measurably reshaped the population of distant small bodies. It is not sending a single wall of ice toward Earth. It is changing probabilities for centuries. Planetary defense programs expand dramatically. New telescopes map near-Earth objects with obsessive completeness. Interceptors are placed in space. The irony is obvious. Humanity cannot deflect the black hole, but the black hole may deflect objects humanity can do something about. So asteroid defense becomes one of the practical responses to an unstoppable event. At 30 years before closest approach, the black hole reaches roughly the neighborhood of 300 AU. The sky still looks normal to the naked eye. There is no black disk growing larger. No stars disappear behind an obvious circle. Gravitational lensing occurs only for favorable alignments, and each event is localized. To most people, the catastrophe remains a date on a calendar. This creates a social problem that no physics model predicted. Fatigue. A generation has grown up with the black hole. Children learned the encounter year before they learned multiplication. News networks have run countdown graphics for decades. There have been political elections, recessions, wars, marriages, divorces, championships, scientific breakthroughs, scandals, and ordinary Tuesdays beneath the same approaching mass. Some people stop paying attention. Others become obsessed. A movement called No After forms among young adults who believe planning beyond encounter year is pointless. Another group organizes around the opposite idea and calls it self-continuity. Its members argue that the very uncertainty of Earth's fate makes long-term planning more important. Most people join neither. They go to work. They complain about rent. They raise children. They make plans for retirement even when retirement comes after perihelion. This may be the most realistic part of the story. Human beings cannot remain at maximum emotional alarm for 50 years. Even an object 10 times more massive than the Sun becomes background if it approaches slowly enough. Elena struggles with this in interviews. Journalists ask whether people have become complacent. She says no. People have become human. Then she adds that complacency and adaptation are not the same. The power plants still need to be built. The orbit measurements still need to continue. But nobody can spend half a century waking each morning as if impact is tomorrow. At 25 years before closest approach, simulations become much sharper. The black hole's perihelion is now predicted to be 5.0 AU from the Sun, with an uncertainty small enough that no plausible solution brings it into the terrestrial planet region. This eliminates one category of nightmare. Earth will not pass near the event horizon. The black hole will not physically cross Earth's orbit. It will not tear Earth apart through direct, close-range tides. At 1 AU from a 10 solar mass black hole, the difference in its gravitational pull from Earth's near side to far side would be only several millionths of a meter per second squared. That is measurable and larger than familiar lunar tidal acceleration in some comparisons, but nowhere near enough to rip the planet into pieces. At 5 AU and beyond, direct body tides are smaller still. The threat is orbital. That distinction finally becomes widely understood. Documentaries stop showing Earth stretching into spaghetti. They begin showing velocity vectors. The pictures are less dramatic. The physics is more frightening. Imagine Earth and Sun as two skaters moving together. A massive passerby pulls on both. If the pull were exactly identical, their relationship would remain almost unchanged. But Earth and Sun are separated by 1 AU. The passerby pulls one slightly differently from the other. Over months, that small difference changes their relative velocity. The effect grows rapidly as distance shrinks. Tidal influence scales roughly with the inverse cube of distance. Cut the black hole's distance in half, and the differential effect becomes about 8 times stronger. This is why the final years matter so much more than the first 40. At 100 AU, the black hole is still far outside the planets, but the tidal acceleration across Earth's orbit is already no longer negligible to precision dynamics. At 20 AU, the situation changes rapidly. At 10 AU, the solar system is in the middle of the encounter. At 5 AU, the approximation of a sun sitting calmly at the center of planetary rings becomes useless. The sun itself is moving hard toward the black hole. This is where the language of a flyby can mislead. The black hole does not simply fly past a stationary solar system like a bullet past a target. The sun and black hole gravitationally deflect one another. With 10 solar masses on one side and 1 solar mass on the other, the sun is the lighter participant. The black hole's speed far away may be 50 kilometers per second. By the time it reaches a 5 AU perihelion, mutual gravity can raise the relative speed to roughly 80 kilometers per second in our chosen scenario. The encounter lasts months at its strongest, long enough for planets to move substantially along their orbits, long enough for the geometry to evolve while the kick is occurring. This is why even 50 years of warning never produces one perfectly simple picture. The event is deterministic in principle. It is not simple. At 20 years before perihelion, Elena's daughter Sophia asks a question Elena has avoided. Sophia is 42. She has a young son. Where should we live when it happens? Elena has advised governments on planetary risk for 30 years. She does not know how to answer her own daughter. Underground shelters do not help against an orbital change. Mountains do not help. Distance from coasts may help with some climate consequences, but not others. Latitude could matter if seasons intensify. A region ideal for cooling is bad for warming. The best location depends on which post-encounter orbit Earth receives. Elena finally says, somewhere with water, energy, food infrastructure, and people you trust. Sophia laughs. That's your scientific answer? It's the honest one. Human survival planning gradually reaches the same conclusion. The black hole is a global risk. There is no hemisphere that can step aside. Resilience matters more than hiding. And the clock keeps moving. 9 years before closest approach, the black hole crosses 100 AU. For the first time, the encounter enters a timescale people can feel. 9 years is a mortgage, a university degree, a child growing from 10 to 19. A government can announce a project and reasonably expect the same adults to see whether it was completed. The black hole is still invisible to the naked eye, but the solar system is no longer behaving normally even by ordinary observational standards. Neptune's orbit is changing fast enough that the difference between old ephemerides and new measurements is obvious to specialists without heroic statistics. Trans-Neptunian objects scatter through orbital element diagrams like filings responding to a magnet, though the force is gravity and the pattern is three-dimensional. Several dwarf planets acquire measurable changes in eccentricity. Some distant minor bodies are already on escape trajectories. The public learns another word: osculating orbit. A planet does not carry a permanent ellipse painted into space. At any instant, astronomers can describe the orbit it would follow if the current gravitational forces suddenly simplified. That instantaneous ellipse is an osculating orbit. During the black hole encounter, the osculating orbits change constantly. News sites try to publish Neptune's new orbit and discover there is no single final orbit yet. The encounter is still happening. At 80 AU, the black hole's weak accretion emission becomes easier to study. Solar wind plasma is sparse this far out, but the incoming object is now moving through material whose properties spacecraft have measured for generations. Researchers attempt to infer how efficiently the black hole converts captured material into radiation. The answer remains uncertain. A black hole with almost no fuel can be nearly dark. A black hole supplied with gas can shine. Our visitor is not feeding on a companion star, so there is no brilliant X-ray binary. Its faint emission becomes scientifically priceless precisely because the environment is unusually well characterized. Probes are sent on deliberately dangerous trajectories. They will not enter the event horizon. There is no need. A spacecraft can study magnetic fields, plasma flow, lensing, and relativistic dynamics from thousands or millions of kilometers away. At those scales, the black hole is still an extraordinary gravitational laboratory. The event horizon remains only tens of kilometers across. One probe, named Faraday, is designed to pass within several 100,000 kilometers if navigation allows. By human standards, that sounds impossibly close. By black hole standards, it is far away. Faraday carries clocks, radiation instruments, particle detectors, laser ranging equipment, and redundant transmitters. Its mission has two purposes: science and trajectory refinement. Every measurement of the black hole's gravitational field reduces uncertainty in what happens to the planets. Faraday becomes the most watched spacecraft ever launched. At 60 AU, it begins transmitting images of a sky subtly distorted around the black hole's direction. There is no black sphere visible against a bright background in the cinematic sense. The angular size of the event horizon from these distances is microscopic. Instead, background stars shift. Some brighten. Their apparent positions trace curves predicted by general relativity. The black hole paints itself with other people's light. Elena watches the first clean astrometric sequence with Sophia and her grandson Matteo. Matteo is 17. He has known about the black hole his entire life. To him, it is less a monster than a deadline. He asks, will Faraday see the event horizon? No. Then why send it so close? Because close is relative. She explains that the region where strong field effects become dramatic is tiny compared with planetary distances. For a non-rotating black hole, the Schwarzschild radius scales directly with mass. One solar mass corresponds to only a few kilometers. 10 solar masses gives roughly 30 kilometers. The black hole could pass through the orbit of the Moon and still have an event horizon far smaller than Earth. But if you fell toward it, Matteo asks, then 30 kilometers becomes very important. Near the horizon, escape becomes impossible. Close enough, tidal forces across a human body become enormous. For a stellar mass black hole, those tides can become fatal before or near horizon crossing. Unlike around the horizon of a supermassive black hole, where local tidal gradients can be gentler. None of that is relevant to Earth in this scenario. Earth will never come remotely close to the horizon. Matteo seems almost disappointed. Popular culture has trained him to expect spaghettification. Real astrophysics gives him orbital dynamics. Then Elena points at Jupiter on the simulation. This is the part you should worry about. 5 years before closest approach, the black hole passes roughly 50 AU from the Sun. Now it is entering the broad region of the Kuiper Belt. Its gravitational influence on outer small bodies is violent. Some objects are flung inward, others outward. A few pass close enough to the black hole to receive extreme slingshots. Astronomers discover bodies leaving the solar system at speeds they never would have reached through ordinary planetary scattering. The black hole becomes a gravitational accelerator. This produces a strange opportunity. A spacecraft passing on the correct side of the moving black hole could gain enormous heliocentric velocity through a gravity assist. For decades, theorists have modeled the idea. Now one mission attempts it. The craft is called Peregrine. It does not approach the horizon. It uses the black hole exactly the way Voyager used Jupiter, except the moving mass is vastly greater. Navigation margins are terrifying. A small error can send the spacecraft somewhere entirely unintended. A larger error can destroy it. Peregrine passes safely. Its velocity relative to the Sun changes dramatically. Within months, it becomes humanity's fastest outbound interstellar probe. The achievement is celebrated. Then commentators ask the obvious question. If a tiny spacecraft can receive such a kick, what happens to planets? The answer has been on the simulations for decades. Now it feels real. 4 years before perihelion, the black hole is around 40 AU away and falling faster. Neptune's future becomes essentially unrecoverable. In most simulations consistent with the final trajectory, Neptune will not remain on anything resembling its old orbit. Some runs eject it into interstellar space. Some temporarily bind it to the black hole. Some throw it inward before later encounters expel it. Uranus has similar problems. Saturn's fate becomes uncertain. Jupiter's fate depends strongly on where the giant planet is when the visitor reaches perihelion. The planetary system is not a row of targets waiting to be struck. Each planet is moving. Jupiter completes an orbit in roughly 12 years. During the final years, it travels a substantial fraction of its path. Astronomers have known Jupiter's exact future phase for decades, so this is not a surprise. In our chosen trajectory, Jupiter is fortunate. At the moment the black hole passes closest to the Sun, Jupiter is not sitting between them. It is on a less catastrophic side of its orbit. Less catastrophic does not mean safe. The black hole still changes Jupiter's velocity relative to the Sun by an enormous amount. One way dynamicists communicate the scale is with a rough hill-like comparison. If a 1 solar mass Sun were placed 5 AU from a 10 solar mass companion in a slow, circular situation, the region where the Sun dominated over the companion would have a characteristic scale only around 1.5 to 2 AU. Our encounter is not slow. It is not circular. It is a fast flyby, so the ordinary Hill-sphere formula cannot predict which planet is stripped. But the number is revealing. Jupiter at 5 AU is far outside that scale. Earth at 1 AU is inside it. The inner solar system is holding on much more tightly than the outer one. This rough picture explains why no credible planning document assumes the giant planets will all stay with the Sun. 3 years before closest approach, the first visible changes arrive for amateur astronomers. Not in the black hole, in the planets. Careful telescope users who compare Jupiter and Saturn against old star charts notice that published planetary positions have drifted from what 20th century ephemerides would have predicted. Of course, modern almanacs already include the black hole. So to see the difference, people deliberately load historical software. They watch 2 solar systems diverge on the screen. One is the system that would have existed. One is the system that does. This becomes a popular classroom demonstration. Children drag a timeline slider. The old Neptune follows its familiar slow arc. The real Neptune peels away. A student asks where it is going. The teacher says, "We don't know what word to use yet." 2 years before perihelion, the black hole is inside 28U. The encounter ceases to be an outer solar system event. Saturn's trajectory is changing rapidly. Jupiter's orbital elements shift month by month. The Sun's own velocity relative to the old solar system barycenter becomes significant. The center of mass of the Sun black hole parallels much closer to the black hole than to the Sun because the black hole has 10 times the mass. Both objects curve around the moving barycenter of their hyperbolic encounter. The phrase "the black hole falls toward the Sun" is now clearly incomplete. The Sun falls much more dramatically toward the black hole. This movement drags the gravitational center of the familiar planetary system through space. The inner planets are trying to remain bound to a star that is itself being accelerated. At 15 AU, Faraday makes its closest scientific pass. The spacecraft is nowhere near the horizon, but the gravitational field is so strong compared with ordinary interplanetary navigation that every second of its trajectory becomes a test of the mass model. Its clocks show relativistic effects exactly where general relativity predicts. Background stars move through lensing patterns. Plasma streams curve. The black hole's mass is refined to better precision than anyone expected at discovery. 10.2 solar masses. The final trajectory is no longer meaningfully uncertain for civilization scale planning. Perihelion, just over 5 AU. Inclination, several degrees to the planetary plane. Relative speed at closest approach, roughly 80 kilometers per second. Earth will be on the side of the Sun that reduces, but does not eliminate, the differential kick. This is one of the better surviving geometries. The world exhales. Then dynamicists show what better means. Earth remains bound to the Sun in the majority of the best-fit simulations, but its orbit becomes substantially more eccentric. The exact final eccentricity still varies because Earth, Moon, Venus, Mars, and the moving Sun interact throughout the encounter. Mars is in greater danger. Jupiter is almost certainly lost from its familiar orbit. Saturn is likely lost. Uranus and Neptune are effectively gone from the old solar system. Better means Earth may still have sunrise. That is the standard now. In the final 18 months, preparation changes character. The science is mostly finished. The work becomes operational. Global grain reserves are distributed instead of concentrated. Artificial agriculture facilities test continuous operation independent of normal seasons. Nuclear plants receive extra fuel inventories and backup systems. Geothermal regions expand generation. Grid operators rehearse a world in which satellites may fail and seasonal demand becomes unpredictable. Medical systems stock critical supplies. Governments duplicate archives in hardened regional centers. Digital knowledge repositories are copied onto local networks that do not require global connectivity. Factories prioritize spare parts for water treatment, power generation, agricultural equipment, and basic medicine. No one knows how badly international trade will be disrupted. So countries attempt to make essential systems less dependent on one distant supplier. This is not autarky. It is redundancy. Space agencies face an uncomfortable choice. Do they keep crews on the Moon? The Moon is gravitationally bound to Earth far more tightly than Earth is bound to the Sun on the scale of the encounter. The black hole's direct differential pull across the Earth-Moon distance at several AU is far smaller than its differential pull across the Earth-Sun distance. Most simulations keep the Moon with Earth, although its orbit can be perturbed. A lunar base therefore shares Earth's fate. Mars is worse. Its solar orbit is less tightly protected, and its location during the flyby is unfavorable in our chosen scenario. Crewed Mars missions are suspended years before encounter. Existing settlers, if our future has any, face a terrible decision. Stay on a planet whose post-encounter orbit is highly uncertain, or attempt the long journey back to Earth before interplanetary navigation becomes chaotic. Most leave. Some remain. There is no single human response to a 50-year warning. At 1 year before closest approach, the black hole is still several AU beyond the giant planets, but accelerating rapidly. The sky surveys tracking it no longer need to hunt for lensing events to know where it is. Its weak accretion emission has strengthened as it moves through denser solar wind. It remains faint compared with stars. Through specialized instruments, however, the invisible visitor is now a persistent source. Faraday's data streams continuously. Peregrine is already far outbound, carrying a record of the old solar system. Elena is 90. She has stopped doing live television interviews. Her hands shake slightly. Her mind remains sharp. Matteo, now 21, works in power system resilience. Sophia has moved the family to a region chosen for water security, grid redundancy, and agricultural infrastructure. Elena moves with them reluctantly. She does not believe the location is safe. She believes safe has stopped being the right word. The last year begins, and for the first time since discovery, the black hole moves quickly enough across the sky that people can watch its gravitational signature change from week to week. The visitor that spent half a century approaching as an abstraction is finally arriving. 6 months before closest approach, the solar system becomes visibly unfamiliar to anyone with good astronomical software. The old planetary map still looks almost normal to the eye because the planets occupy roughly the same broad regions. But the velocity arrows tell the truth. Neptune is no longer moving like a planet comfortably bound to the sun. Uranus is being pulled onto a radically altered path. Saturn's future changes from one simulation frame to the next as the black hole's passage turns a once stable ellipse into a gravitational encounter. Jupiter has become the central uncertainty of the giant planets, and the Sun is accelerating. On Earth, nobody feels that acceleration directly. This is important. If Earth and everything on it are pulled almost equally in one direction, you do not feel yourself being dragged through space. You feel local gravity from Earth. You feel the floor. You feel the chair. You do not feel the Sun and Earth together changing velocity around the black hole. What matters physically and biologically is differential acceleration. The black hole pulling Earth differently from the Sun, the Moon differently from Earth, one side of Earth differently from the other. At this distance, the direct tidal stretching across the human body is effectively irrelevant. The direct tidal stretching across Earth is not the main threat either. The entire planet is not about to be torn apart. The dangerous differential is the one across astronomical units. The distance between Earth and Sun is enormous compared with the size of Earth. The black hole can change that relationship significantly while leaving the planet itself intact. This is why people on the ground experience an eerie mismatch. The greatest gravitational event in recorded human history feels like an ordinary morning. Coffee remains in cups. Rain falls downward. Birds fly. The horizon does not tilt. And in a control room, a number representing Earth's future orbital energy changes every hour. For months before perihelion, the first outer planet is effectively lost. Neptune's heliocentric orbital energy becomes positive in the dominant simulations and then in direct measurement. That phrase sounds technical. Its meaning is simple. Relative to the Sun, Neptune is escaping. There is no explosion, no collision, no moment when the planet crosses a glowing boundary. Neptune simply has too much energy to remain on a closed orbit around the Sun. Its path is now open. It will continue outward. Depending on the exact encounter, it may spend time influenced by the black hole, but it no longer belongs to the solar system in the old sense. Humanity watches the last days of Neptune as a solar planet through telescopes. The planet itself does not know anything happened. Its atmosphere remains blue. Its moons continue orbiting for now, though their long-term stability depends on the changed gravitational environment. Triton crosses the images as a tiny moving point. People hold public vigils. Elena refuses the word funeral. Neptune isn't dying, she tells Matteo. It's changing address. 2 weeks later, Uranus receives its decisive kick. Its outcome is stranger. For a time, the planet is neither comfortably bound to the sun nor cleanly free. The black hole's moving gravitational field bends its trajectory strongly. Models suggest it will ultimately leave with a velocity and direction unlike Neptune's. The two outer planets that spent billions of years in ordered orbits become independent wanderers within weeks of one another. Every textbook diagram of the solar system becomes historical. The public begins referring to the old eight. Astronomers dislike the phrase. It persists anyway. 3 months before perihelion, Saturn's orbit changes enough that naked eye observers can eventually detect a positional difference from the path printed in old almanacs. The difference is still subtle, but it exists. Amateur astronomers organize comparison nights. They use century-old orbital tables and modern coordinates. The planet is not where history expected it to be. The black hole remains invisible to ordinary eyes. Saturn becomes the visible proof. At this stage, the sun-black hole relative speed has risen well above the distant 50 km/s value. The geometry changes day by day. The black hole approaches from above the planetary plane at a shallow angle. Its track on the sky passes through constellations that cultures have watched for thousands of years. There is still nothing to see without instruments. People go outside anyway. They point. Somewhere there. A location in darkness acquires emotional weight simply because everyone knows what occupies it. 2 months before perihelion, Jupiter experiences its strongest pre-encounter acceleration. The giant planet's immense mass does not protect it. In gravitational acceleration, mass of the falling object cancels out. A feather and a planet respond to the same external gravitational field in the same way if other forces can be neglected. Jupiter's mass helps it hold its moons. It does not make the planet harder for the black hole to accelerate through space. The Galilean moons remain gravitationally bound to Jupiter in many simulations because they orbit deep inside Jupiter's own gravitational well. But Jupiter's orbit around the Sun is another question. The black hole pulls. The Sun moves. Jupiter moves. All three interact. The final outcome has become clear enough to hurt. Jupiter will not remain on its old 12-year orbit. Whether it remains bound to the Sun at all depends on a narrow range of encounter geometry. In our chosen branch, it does not. Jupiter is going to leave. The announcement is made without drama by an international dynamics center. Measurements now show that after the encounter, Jupiter's energy relative to the departing Sun will be positive. The largest planet will become a rogue planet carrying at least some of its moons into interstellar space. For people alive before the black hole's discovery, this seems impossible. Jupiter felt like part of the definition of the solar system. It is older than humanity, older than mammals, older than Earth in anything like its present form. Yet gravitationally, permanence was always conditional. Jupiter belonged to the Sun because its velocity and position kept it bound. Change those. The relationship ends. This gives the public a more accurate picture of what the black hole is doing. It is not eating the solar system. It is unbinding it. At 6 weeks before perihelion, the black hole's faint high-energy emission becomes easier to detect, though it is still nowhere near the blazing disk of an actively feeding binary. The solar wind thickens inward. Material falling toward the black hole heats. Magnetic processes become complicated. Researchers argue about models in real time. The event is the greatest nearby laboratory for isolated black hole accretion ever available. Faraday is now transmitting with delays measured in hours rather than days. The probe's cameras cannot photograph an event horizon as a resolved circle, but its instruments map the plasma environment with extraordinary detail. One experiment sends precise laser pulses and radio signals along paths passing relatively near the black hole. The timing shifts as space-time curvature delays and bends the signals. General relativity has passed tests for more than a century. The black hole does not reveal that Einstein was wrong in some spectacular, easy way. Instead, the measurements agree beautifully within precision. There is something almost frustrating about this. A cosmic catastrophe arrives, and the equations continue working. Elena finds that comforting. Physics is not panicking. People are. At 1 month, schools close in many places. Not because the black hole emits dangerous radiation toward Earth, because transportation, emergency services, and families are entering in counter protocols. Governments reduce non-essential travel. Markets suspend some forms of trading. Military forces move to protected communication states, partly because satellites may soon become unreliable. Some satellites in Earth orbit are unlikely to be stripped directly because they are tightly bound to Earth, just as the Moon is. But the changing Earth-Sun geometry can affect navigation systems, solar illumination, ground station pointing, and the broader space infrastructure. Satellites at very high Earth orbits and delicate libration point missions are more vulnerable to changes. Spacecraft near Sun-Earth Lagrange points no longer inhabit the same clean gravitational geometry on which their station-keeping plans were based. Several are moved or abandoned. The old Lagrange point maps are becoming obsolete before people's eyes. 3 weeks before perihelion, Mars receives a strong perturbation. Our fictional geometry is bad for Mars. The planet is positioned on the side of the Sun that amplifies the differential kick. Its orbit stretches dramatically. For several days, models disagree over whether it will remain bound. Then the answer settles. Mars remains associated with the Sun for the immediate future, but on an enormous, elongated orbit crossing regions it never approached before. That may not be stable once the remaining planets interact. Any human settlement there would face extreme changes in solar energy over future years. Earth watches this and understands how narrow its own good fortune is. Earth happens to be positioned in a less destructive phase. Not safe, less destructive. The Moon remains bound in essentially all of the best simulations. That matters for tides and for psychological continuity. One familiar companion is likely to stay. Venus and Mercury also remain tightly connected to the Sun in most of the best fit runs. The inner system may survive as a damaged family after the outer system is stripped. 2 weeks before closest approach, a new number dominates every broadcast. Delta versus change in velocity. Spaceflight engineers have used the term forever. Now billions of people know it. Earth moves around the Sun at nearly 30 kilometers per second. A change of only a few kilometers per second in Earth's velocity relative to the Sun can radically alter the orbit. A rough tidal impulse estimate for a 10 solar mass object passing several AU away at tens of kilometers per second produces exactly that worrying scale. Several kilometers per second, not 30. Not enough in our geometry to guarantee ejection. Enough to matter enormously. The direction of the velocity change is as important as its size. Push along Earth's orbital motion and the orbit gains energy. Push against it and the orbit loses energy. Push sideways and the ellipse rotates and changes shape. Because the black hole's path, Sun's motion, and Earth's position are all known, this is no longer abstract. The best numerical integrations show Earth's post-encounter orbit remaining closed around the Sun. Its year will change. Its eccentricity will increase. The amount of sunlight received over the orbit will vary more than before. The result will be a climate shock, not immediate planetary sterilization. That is the survivable branch we will follow. It is not guaranteed by the words, black hole enters the solar system. A slightly different trajectory could eject Earth. A closer passage could do far worse. A more distant passage might leave Earth almost untouched while still disturbing comets. Mass matters. Distance matters. Geometry matters. Our story has finally selected one path through the possibilities. 10 days before perihelion, the Sun's apparent motion against the background of distant radio sources shows its acceleration unmistakably. Nobody looking at the Sun from Earth sees it shoot across the sky because Earth is moving too. But the solar system's trajectory through the galaxy has changed. The Sun is being gravitationally slingshot by the heavier intruder. This raises a strange question. Afterward, what is the solar system moving relative to? There is no absolute rest. Astronomers describe velocities relative to the local standard of rest, nearby stars, the galaxy, and the black hole. The familiar idea of the Sun traveling serenely around the Milky Way remains approximately true on galactic scales, but its local velocity receives a substantial new component. The flyby changes not only which planets remain with the Sun, it changes where the surviving system is headed. 5 days before perihelion, Faraday passes through the most dangerous part of its planned trajectory. The probe is much closer to the black hole than any planet will be. Its signal becomes one of the most valuable streams of scientific data ever received. There is no final cinematic photograph. There is a sequence of measurements. Increasing gravitational redshift, changing plasma conditions, precise timing, star fields distorted in ways that look almost fluid when plotted. The probe transmits until a communications geometry problem interrupts the link. For 6 hours, the world assumes Faraday is gone. Then the signal returns. Elena cries. She has known people who died during the 56 years of preparation. Colleagues, friends, her husband, years earlier. Yet somehow this machine's return feels like a message from all of them. The probe was built by people who knew they would probably not live to see perihelion. Its engineers designed components that younger engineers learned to maintain. Its mission passed through generations. The black hole has turned scientific planning into a form of inheritance. 48 hours before perihelion, Jupiter's old orbit is effectively over. The planet has not yet escaped far away. It remains visible, but its velocity relative to the Sun now places it on an open trajectory. Saturn is also being stripped in the dominant solution. Humanity has lost the outer solar system before the black hole even reaches closest approach. On Earth, direct physical sensations remain ordinary. The difference between cosmic violence and local calm becomes almost unbearable. Elena sits with Sophia and Matteo in a control center that is part research facility and part emergency shelter. There are no giant windows. No reason to watch the sky directly. Data cover the walls. Earth-Sun distance. Earth's instantaneous velocity. Lunar orbit. Solar flux. Grid stability. Satellite health. The black hole's distance. One screen shows the trajectory in astronomical units. Another shows it in kilometers. The number is still hundreds of millions. Matteo looks at Elena. Is this the closest you've ever been to one? She laughs softly. By several thousand light years. The room laughs too. Nervous laughter. Elena is 91 now. She was 34 when a background star moved the wrong way. For more than half her life, this date has existed in the future. Now it is 2 days away. She finds that the feeling is not fear exactly. It is exhaustion meeting awe. 24 hours. The black hole is racing inward at a relative velocity, now approaching the expected perihelion value. The Sun is racing too. The system is a gravitational two-body encounter surrounded by smaller bodies struggling to decide which mass, if either, they remain bound to. A useful way to picture the final day is to stop imagining the planets as beads on fixed rings. There are no rings. There are positions and velocities. Every planet is falling through a changing gravitational landscape. Mercury and Venus remain close to the Sun, Earth, and Moon move together, but their heliocentric path bends. Mars is being pulled onto a stretched future. Jupiter and Saturn are leaving. Uranus and Neptune are already gone from any recognizable version of the old system. Countless asteroids receive new orbital elements. Some become more dangerous. Others are ejected. The asteroid belt does not instantly dissolve, but its long-term stability is shattered. The black hole passes close enough to Jupiter's old orbital radius that families of small bodies undergo enormous scattering. Planetary defense networks begin tracking thousands of new objects. Most will never hit Earth. A tiny fraction may matter years later. The encounter has a long tail. 12 hours. Direct solar brightness at Earth begins changing slightly, not because the sun is dimming, but because Earth-Sun distance and relative motion are departing from the old orbit. The difference is initially small. Weather systems do not suddenly collapse. Plants do not notice a new orbit in an afternoon. Climate responds over time. Ocean heat capacity provides inertia. So does ice. So does soil. The immediate danger on Earth comes more from human systems reacting to uncertainty. Financial networks, transportation, emergency communication, power demand, misinformation. Governments have spent decades planning for this day, and even so, rumor outruns physics. A false message claims the moon has been lost. It has not. Another claims gravity on Earth has changed by 20%. It has not. Earth's own surface gravity is dominated by Earth's mass. A distant black hole mostly accelerates the whole planet together. Another rumor claims the atmosphere will be sucked away. It will not. The atmosphere is gravitationally bound to Earth and travels with the planet. The black hole is not close enough to strip it directly. Elena records a short public message. She does not say everything is safe. It is not. She says what is true. Earth is intact. The moon is with us. The sun is still shining. We are entering a new orbit, not falling into an event horizon. The message is replayed billions of times. 6 hours. The black hole is near the distance of Jupiter's old orbit from the sun. The sun's acceleration is enormous by astronomical standards. Because the black hole is 10 times more massive, the sun's hyperbolic deflection is dramatic. The relative speed of the two masses approaches roughly 80 kilometers per second. The strongest phase lasts not a second, but many weeks, with these hours marking the closest geometry. Earth's relative velocity to the sun changes continuously. Dynamicists watch the final orbit emerge. Not all at once. A post-encounter orbit is meaningful only after the disturbing mass begins receding enough that the sun once again dominates Earth's long-term motion. But the signs are encouraging. Bound. The word appears on internal simulation dashboards. Then public ones. Earth remains solar-bound. People cheer. Elena does not yet. Bound is not the same as familiar. 2 hours. Saturn crosses the mathematical threshold into an unbound heliocentric trajectory in the best fit solution. The ringed planet will leave with much of its satellite system. There will be complicated moon losses and captures. Future astronomers will spend decades determining what remained attached. The Sun has now lost all 4 giant planets in our chosen branch: Jupiter, Saturn, Uranus, Neptune. The old architecture is gone. The inner worlds remain. An hour. The black hole itself is at perihelion, 5 astronomical units from the Sun, hundreds of millions of kilometers from Earth. Nothing crosses an event horizon except sparse gas, and whatever tiny debris happens to fall sufficiently close. No planet is swallowed. No star is torn apart. No beam of death sweeps Earth. Instead, Gravitational trajectories reach the turning point of a cosmic encounter. The black hole's path curves around the sun-black hole barycenter. The sun's path curves much more. Then the distance begins increasing. 1 minute after calculated perihelion, nothing on Earth looks different. 1 hour after, nothing on Earth looks different. And yet the solar system humanity inherited from 4.5 billion years of history no longer exists. The black hole is leaving. The damage is still arriving. The first day after perihelion is mostly about waiting for the equations to become simpler again. The black hole is receding. That is the good news. It remains enormously influential, but every hour increases its distance from the sun. Its gravitational effect does not switch off. It fades. The sun, Earth, moon, remaining planets, asteroids, and escaping giant planets all carry velocities acquired during the encounter. The future is now stored in motion. By the end of the first week, dynamicists can describe Earth's new solar orbit with much greater confidence. For our survivable branch, the orbit is no longer nearly circular. Its closest distance to the sun will be somewhat less than today's Earth-Sun distance. Its farthest distance will be substantially greater. To keep the story physically plausible without pretending we have run a uniquely determined simulation, imagine a representative post-encounter orbit with perihelion a little above 9/10 of an AU and aphelion a little above 1.2 AU. The exact numbers are not the lesson. The range is, at closest approach to the sun, Earth will receive noticeably more sunlight than today. At farthest distance, substantially less. Because solar intensity scales with the inverse square of distance, a modest-looking change in orbital radius produces a large change in received energy. Earth's new year is also longer because the average orbital distance has increased. The planet remains habitable in the simple sense that liquid water does not instantly disappear and the atmosphere remains intact. But the climate system has been handed a forcing unlike anything human civilization has experienced. And orbital eccentricity is only one part of the problem, where perihelion falls relative to Earth's axial seasons matters. If one hemisphere's summer occurs near perihelion, that hemisphere receives an especially strong seasonal pulse. If winter occurs near aphelion, the cold season is enhanced. Precession gradually changes that alignment over long times. The oceans buffer temperature changes, but they cannot erase them. Ice responds. Atmospheric circulation responds. Monsoons respond. Storm tracks respond. Ecosystems respond. Agriculture responds. The first post-encounter year, therefore, becomes the most heavily monitored year in history. There are no historical climate analogs with exactly the same forcing. Models help. Observations decide. At first, the immediate temperature changes are smaller than some people expect. Oceans hold enormous amounts of heat. Soil and ice have thermal inertia. The atmosphere does not jump instantly to equilibrium with a new orbit. Then Earth begins moving farther from the sun. The first extended cool phase arrives. Northern agricultural regions experience growing seasons unlike their old calendars. Some crops fail. Others perform better in regions that prepared. Artificial agriculture, once criticized as expensive planetary emergency spending, becomes critical. Greenhouses operate under controlled light. Indoor farms produce vegetables and seed stock. Staple calories still come largely from conventional agriculture where possible, but crop belts shift. Global food trade is chaotic. Countries that spent decades building reserves and resilient energy systems fare better. Countries that did not suffer more. Human deaths come not from the black hole directly, but from familiar vulnerabilities magnified by an unfamiliar climate. Power failures, food shortages, political conflict, migration, disease after infrastructure disruption. The cosmic cause is exotic. The human consequences are painfully ordinary. Elena watches all of this from a world that still feels like Earth. That matters. There are birds outside, rain, television, traffic. People complain about government policy. Children go back to school. The world has not become a frozen rogue planet, but the calendar is being rewritten. Meteorological agencies stop using some old seasonal averages because the reference climate no longer describes the new orbital forcing. Farmers learn to plan by orbital phase. Solar energy operators integrate distance from the sun into forecasts in ways that once mattered only as a small annual correction. The phrase perihelion season becomes part of ordinary weather conversation. Months after the flyby, Mars crosses farther outward on its stretched orbit. Jupiter and Saturn continue receding on open paths. They have not vanished. Telescopes still see them. For years, Jupiter remains a bright object, though its motion no longer repeats the familiar 12-year cycle. It becomes a wanderer with a known origin. Future astronomers will be able to calculate backward and say, "This rogue planet was once ours." The concept is emotionally strange. Astronomers have discovered free-floating planetary mass objects elsewhere. Now humanity has watched worlds become rogues in real time. Uranus and Neptune are farther away and harder to follow. Their trajectories become long-term observational projects. The black hole itself may carry some minor bodies away. It might temporarily capture debris. In our branch, it does not permanently capture the Sun or any of the terrestrial planets. Its incoming speed was too high, and the encounter lacks a mechanism to dissipate enough orbital energy for a clean two-body capture. Three-body exchanges can rearrange smaller objects, but the black hole remains a galactic passerby. Within a year, it is well outside the giant planet region again. Its weak accretion emission begins fading as solar wind density drops. The scientific opportunity is leaving almost as quickly as it arrived. Faraday continues transmitting. Its orbit relative to the black hole was designed to let the probe escape rather than cross the horizon. The spacecraft survives the encounter and becomes a follower for a time, using the black hole's motion as a moving laboratory. Eventually, power and communications limits will end the mission. Before that happens, it sends measurement scientists will study for generations. General relativity survives another severe test. Models of low-rate black hole accretion improve. Measurements of gravitational lensing become exquisitely precise. Researchers estimate the black holes spin more tightly through its influence on nearby plasma and relativistic signals, though doing so is far harder than measuring mass. The object that nearly dismantled the solar system becomes one of the best-studied stellar black holes in the galaxy. There is an uncomfortable beauty in that. Humanity learns more because it was endangered. It would have preferred ignorance and safety. Science does not require catastrophe. But when catastrophe arrives, science turns observation into understanding because that is one of the things humans know how to do. The second post-encounter year is harder than the first in some regions. The initial reserves are smaller. Infrastructure built for a pre-encounter world is wearing out under new climate demands. Migration intensifies. Coastal regions face changes not because a gravitational wave struck them, but because altered climate modifies storms, precipitation, snowpack, and eventually ice balance. Sea level does not respond instantly to the orbital kick. Glaciers take time. Ocean circulation takes time. Every system has its own clock. This becomes another lesson of the flyby. The gravitational event lasted months at strongest influence. Its consequences operate on seconds, years, centuries, and millennia. Some asteroid orbits changed immediately. Some collision risks emerged decades later. Some Oort cloud comets redirected during approach may arrive centuries or thousands of years later. Climate responds across seasons and centuries. The loss of giant planets changes long-term, small-body dynamics for millions of years. A solar system can be transformed quickly and continue discovering the meaning of that transformation long afterward. Planetary defense astronomers inherit one of the most difficult jobs. The asteroid belt was disturbed. Jupiter is gone. For generations, Jupiter was often described casually as Earth's shield, sweeping dangerous objects away. That description was always too simple. Jupiter can eject comets from the solar system, but its gravity can also redirect bodies inward. Removing Jupiter does not translate into one simple increase or decrease in impact risk. What matters now is that the entire small body environment has changed. Orbits must be remapped from scratch. Thousands of objects once considered stable no longer are. Some resonances disappear. New ones form among the surviving planets. Mars's altered orbit intersects regions it never crossed. Space agencies launch an armada of survey telescopes. Humanity survived one large gravitational threat only to inherit many smaller ones. Unlike the black hole, these can sometimes be deflected, so planetary defense becomes permanent infrastructure. 5 years after perihelion, the black hole is far beyond the major planets and receding quickly. From Earth, its lensing signature becomes harder to study. The object grows scientifically distant. Public attention moves on. The black hole that dominated every childhood conversation for a generation becomes history while still being nearby on galactic scales. Elena is 96. She cannot travel easily now. Her hearing is poor. Matteo visits with portable displays showing the latest trajectory fits. The black hole is never returning. Not on any human timescale. Its hyperbolic path carries it back into interstellar space. It will wander the Milky Way. Perhaps one day, millions of years from now, it will pass near another star. Perhaps not. Galactic space is vast. Matteo asks Elena whether she feels relieved. She says yes, then adds, "I miss measuring it." He laughs. Only an astronomer could miss an object that destroyed the old solar system. But Elena does. For 60 years, the black hole gave her life a direction. Every new data mattered. Every reduction in uncertainty mattered. Now the unknown object is known and leaving. The emergency that defined generations has become an archive. A year later, Elena returns virtually to the survey field where the first microlensing event occurred. The original background star is still there. It was never physically involved with the black hole. It was far behind it. Its light merely passed through curved space-time on the way to Earth. The star looks ordinary again. Its apparent position no longer carries the dramatic deflection that first alerted Elena. She watches a plot overlay the old data. A tiny curve, a star that seemed to move. A black hole 600 AU away. 57 years of warning. For giant planets gone. Earth on a new orbit. All of it hidden inside one small deviation on a graph. This is when Elena finally appreciates how lucky humanity was to notice the object when it did. Was detection guaranteed? No. That is worth saying clearly. An isolated black hole can be extraordinarily difficult to find. If it emits little or no radiation, astronomers need its gravity to reveal it. Microlensing requires a favorable alignment with background sources. Astrometric lensing becomes easier for a nearby massive object because the effect can be large, but someone still has to measure the relevant star field. Planetary perturbations become unavoidable once a 10 solar mass object comes sufficiently close. Yet exactly how much warning they provide depends on distance, approach direction, data precision, and the object's velocity. Our story gave humanity an unusually favorable early lensing discovery at 600 AU. Another geometry might provide less warning. A black hole approaching through a sparse background field, moving faster, or following a less obvious early perturbation pattern could remain unidentified longer. The claim that astronomers would certainly know centuries in advance is too confident. The opposite claim, that an invisible black hole could appear tomorrow without any gravitational warning until it crossed Earth's orbit, is also wrong for our massive close visitor. Gravity leaves evidence. The question is when we recognize it. Elena's first paper about the object becomes a classic because its conclusion was so cautious. The final sentence did not say a black hole was coming. It said the data were inconsistent with any luminous object of the inferred mass and distance and required urgent follow-up. Science reached the terrifying conclusion by refusing to jump to it. That becomes part of the cultural memory of the event. People later tell simplified stories. Elena discovered the black hole. In truth, no one person did. A survey detected the first event. Software flagged it. Technicians calibrated instruments. Other telescopes confirmed it. Dynamicists connected it to orbital residuals. Engineers tracked spacecraft. Thousands of researchers refined the path. Public agencies built resilient systems. Farmers changed crops. Grid operators built redundancy. Doctors stocked medicines. People who never looked through a telescope helped civilization survive a black hole. This mirrors the deeper truth of planetary defense. Detection is only the first act. Understanding, communicating, planning, and adapting are separate forms of work. 10 years after perihelion, Earth has learned its new rhythm. The climate has not stabilized completely. It may not for a long time. But civilization has adapted enough that children born after the encounter experience the new year as normal. Their calendars are different. Seasonal traditions move. Agricultural regions have shifted. Some former farming zones are marginal. Others have become valuable. Energy systems are built around greater orbital variability. People still use the old phrase 1 year, but the number of days no longer matches the pre-encounter year. There are political arguments about whether to preserve historical month lengths or redesign the calendar completely. Humanity survived a black hole and immediately began fighting about the calendar. Elena finds this deeply reassuring. Normal life is not silence after catastrophe. It is argument returning. The moon remains. Its orbit changed somewhat during the encounter and has been carefully remeasured. Tidal calendars changed. Coastal communities adapted. The moon's presence stabilizes something psychological even when its exact orbital parameters differ. People look up and see a familiar disk. The giant planets are not visible where old astronomy books say they should be. Jupiter remains observable with telescopes for a long time as it recedes. Eventually, it becomes faint. Saturn too. Future generations may launch missions after them, not to bring them back, to study the worlds the solar system lost. There are serious proposals for a Jupiter farewell probe using nuclear power and high-speed propulsion. The journey is enormous because Jupiter is no longer orbiting and returning. Every year it is farther away. A mission to a rogue Jupiter would be more like an interstellar precursor than an ordinary planetary mission. The idea fascinates Matteo. Elena tells him to go. Me? You spent your whole career keeping the lights on. That's useful. So is going after Jupiter. He does not become an astronaut. He joins the engineering team that designs the probe's power system. The black hole keeps rearranging lives long after it leaves. And somewhere far beyond the surviving planets, Peregrine is moving rapidly into interstellar space, accelerated by the intruder. It carries a simple plaque showing two versions of the solar system. Before, after. Not because anyone expects aliens to find it. Because humans needed to mark the boundary. One system existed, then another did. 10 years after perihelion, Elena is 101. She is invited to a classroom whose students were born after the encounter. For them, the solar system with 8 familiar planets is not a lost childhood landscape. It is history. Their classroom model shows Mercury, Venus, Earth, and the radically altered path of Mars around the Sun. For dashed trajectories peel away into the dark, marking the giant planets that once belonged to the system. Elena stands beside the model with a cane in one hand. The teacher has prepared a presentation. Elena ignores it. Questions, she says. A hand goes up immediately. Why didn't the black hole suck Earth in? Elena smiles. She has answered some version of this question for almost 70 years. Because black holes don't have special vacuum cleaner gravity. The student looks disappointed, which makes several classmates laugh. Elena points at the black dot on the model. If you replaced an ordinary object with a black hole of exactly the same mass, then far away from it the gravitational pull would be essentially the same. What makes a black hole unusual is that enormous mass can be compressed into a tiny region. You can get much closer to the center of that mass than you could with a normal star. She points at the marked perihelion. Our visitor had about 10 times the mass of the Sun. If it had been a normal object with 10 solar masses passing on the same path, the planetary problem would still have been catastrophic. So the fact that it was a black hole didn't matter? It mattered enormously if you were foolish enough to go close to the event horizon. The room laughs. But at planetary distances, the mass was the main problem. She draws 2 circles on the board, one large enough to represent 5 astronomical units. The other is impossible to draw to scale. For 10 solar masses, the event horizon would have been only around 30 kilometers in radius. 5 astronomical units is about 750 million kilometers. She pauses. If I drew the 5AU encounter across this entire building, the event horizon would still be too small for this marker to show accurately. A child near the front says, but it's still through Jupiter away. Exactly. That is the scale that has fascinated Elena all her life. Geometrically tiny, dynamically enormous. Another hand rises. Would it have been worse if it was bigger? Yes. How much bigger? There isn't one answer. If the same path belonged to a 1 solar mass black hole, the disturbance would have been much weaker. If it belonged to something 30 times the mass of the Sun, much stronger. If you imagine thousands of solar masses passing at 5AU, you would no longer be telling our survivable version of the story. So mass matters most. Massachusetts' closest distance, speed, and geometry. She holds up 4 fingers. Those are the numbers I would ask for before believing anybody who told me exactly what a black hole entering the solar system would do. She lets the students consider that. A black hole passing through the distant Oort cloud is one story. One passing hundreds of AU away is another. One crossing near Neptune is another. One passing between Earth and the Sun is another. The words black hole are not enough. A boy at the back raises his hand. How did you see it if it was black? We didn't see the hole itself. Elena points toward an old plot projected on the wall. A background star curves slightly from the position it would otherwise have occupied. We saw what its gravity did. She tells them again about the first star. The smooth microlensing brightening. The astrometric shift. The missing luminous object. The small discrepancies in distant orbits. In the real science known before the encounter, isolated compact objects had already been found or constrained through gravitational microlensing, while other dormant black holes had been discovered because visible companion stars moved around unseen masses. Their visitor was easier in one sense and harder in another. It was vastly closer than any previously known stellar black hole, but it had no ordinary companion star pointing toward it. So would we always get 57 years? A student asks. No. That answer quiets the room. Our discovery was lucky. She explains that microlensing requires useful geometry. A dark object has to pass close enough to a background source on the sky for the bending to become measurable in a survey that is actually observing that region with sufficient precision. Astrometric effects extend over a wider angular range, especially for a very nearby massive lens, but telescope coverage, cadence, star density, and data analysis still matter. Planetary perturbations would eventually reveal a 10 solar mass object crossing the planetary system, but eventually is not the same as at 600 AU. If it had approached through a different part of the sky, Elena says, we might have found it later. If it moved faster, we would have had less time. If it were less massive, the early perturbations would have been smaller. So we could have had no warning. Not literally no gravitational warning once something that massive became close enough. But we were never entitled to exactly the warning we got. The teacher looks toward Elena. She knows this is not the reassuring answer adults often prefer giving children. Elena has never been good at false reassurance. On the other hand, why didn't the black hole stay? This question makes her smile. Because gravity doesn't automatically capture things. The students know gravity pulls. They have grown up seeing the consequences of the most dramatic pull in human history. So the idea that two gravitating objects can meet and then separate feels strange. Elena walks slowly toward the model. Imagine the black hole approaching from interstellar space with a high speed. As it fell toward the sun, gravity accelerated the relative motion. Around closest approach, the path curved strongly. As the objects separated, gravity slowed the outward relative motion again. But if the sun pulled it, why didn't it stop? Because it arrived with enough orbital energy to remain unbound. In a simple two-body encounter, with no mechanism to remove that energy, the path is hyperbolic. It comes in and goes out. She taps Jupiter's dashed line. The smaller bodies complicate the encounter because three bodies can exchange energy. A planet can be ejected. A planet can sometimes be captured by the visitor. But the black hole itself was carrying enormous momentum. Our planets did not conveniently break it into a quiet orbit around the sun. Another student points at Earth. Why did Earth stay when Jupiter didn't? Because where you are matters. This becomes the next drawing. Elena sketches the sun and two imaginary Earths on opposite sides. People often remembered only one number from the forecast, 5 AU, closest approach to the sun. But Earth was not sitting inside the sun. Earth was 1 AU away and moving at almost 30 kilometers per second. She draws velocity arrows. The black hole pulled the sun and Earth both. What changed our orbit was the difference between those pulls, integrated through the encounter. She moves one imaginary Earth to the opposite side. Put Earth somewhere else in its orbit and the direction of the velocity kick changes. Change the black hole's inclination and it changes again. Move Jupiter to another phase and its outcome changes. So we were lucky? Very. Could Earth have been thrown away? Yes. No hesitation. The classroom is silent again. In a different geometry, Earth could have left the sun. In another, it could have ended much closer to the sun. In another, the orbital change might have been modest. Our branch left Earth-bound, but on a more eccentric orbit. The students have never known the old seasons except through recordings. For them, orbital phase agricultural forecasting is ordinary. What would happen if Earth got thrown out? Elena leans against the desk. Earth itself would not immediately explode. The atmosphere and oceans would remain attached at first, but sunlight would fall rapidly as the planet moved away. The surface climate would eventually become far colder. Maintaining a large civilization would depend on artificial energy, enclosed habitats, geothermal or nuclear power, and enormous engineering. Could people live? Some might, with enough preparation and functioning technology. But keeping billions of people alive on a rogue Earth would be far harder than surviving the orbit we actually received. The teacher says, that brings us to the question everyone writes in essays. Elena knows which one. Could humanity have left? A student asks it anyway. Could we just have built spaceships? Elena turns toward the window. She has always loved this question because it reveals the difference between distance and habitability. A spacecraft can leave Earth much more easily than Earth can leave danger. But space is not automatically safer. She counts what Earth gives a human without permission. Air, water, radiation shielding, gravity, an enormous thermal buffer, soil, industry, hospitals, a biosphere, billions of other people maintaining specialized systems. An ark has to reproduce those functions with machines, she says. And if you launch at tens of kilometers per second, decades give you hundreds of AU of travel, not another habitable planet. One student points at the black hole trajectory. But couldn't you go the other way? You could choose trajectories that reduce particular risks. You could launch small populations. Advanced propulsion would help. We did launch habitats and scientific craft. But there was no nearby second Earth sitting just outside the encounter. The Moon shared most of Earth's fate. Mars, in our geometry, worse. The student frowns at Mars's long orbital line. So staying was safer? For most people, yes. Provided the models still gave Earth a good chance of remaining habitable. Elena looks toward the old photographs on the classroom wall. Farms under artificial lighting. Grid projects. Water reservoirs. Seed facilities. Emergency hospitals. The best planetary defense we had was not a weapon. It was making one planet harder to kill. Another hand rises. Why didn't we move Earth instead? That question has followed Elena since the first school she visited, decades before perihelion. She remembers the boy who asked it when she was still middle-aged. She gives almost the same answer. It was the right kind of question. Then the scale, Earth's mass, the required momentum. The fact that humans can change asteroid trajectories slightly and spacecraft trajectories enormously, but a planet is another category. Over very long periods, sufficiently advanced civilizations might imagine repeated gravitational encounters with asteroids or other megastructural methods to change a planet's orbit. 57 years was not that kind of timescale. Could we move the black hole? Several children laugh before she answers. No, not even with nuclear bombs. No, all of them. No, the certainty delights them. There are few questions in astronomy where a scientist can answer that cleanly. 10 solar masses is an absurd amount of inertia. We had no technology capable of changing its trajectory enough to matter. A girl asks, then what was the point of knowing? Elena turns toward her. This is the question beneath almost every other one. If you can't stop something, why measure it? She thinks of 57 years. Of people who spent careers on projects whose final purpose they would not live to see. Because stopping a danger is only one kind of action. She talks about hurricanes, earthquakes, volcanic hazards. Some things are not prevented. They are forecast. Buildings change. Food is stored. People move. Systems gain redundancy. A warning can save lives without eliminating the source of danger. We couldn't tell the black hole to leave. We could decide what kind of civilization it encountered. The girl seems satisfied. Then someone asks about the new seasons. Did the black hole change the sun? Mostly, it changed our relationship to the sun. At 5 AU, the black hole was far too distant to tidally tear the sun apart in the way a near encounter could. The sun continued producing light, but Earth's orbit changed. Solar energy received by a planet depends strongly on distance. Move closer, and the same star becomes more intense. Move farther away, and it becomes weaker. Our fictional post-encounter orbit gave Earth a larger annual swing. The oceans buffered some of the immediate temperature response. Atmosphere, ice, circulation, ecosystems, and agriculture responded over different timescales. That is why there was no single day when the climate became the new climate. The gravitational kick was fast. The climatic meaning unfolded over years and decades. And the comets? A student asks. Elena points beyond Neptune's old orbit. Or rather, where Neptune's old orbit is displayed in pale gray. Some consequences are slower still. A black hole can perturb a distant icy body and leave long before that body reaches the inner solar system. The Oort cloud extends so far that orbital periods can be enormous. Some objects redirected during the approach may not become relevant for centuries or millennia. The asteroid population also inherited new orbits when the giant planets disappeared from the old configuration. Jupiter's role had never been as simple as the popular claim that it was Earth's shield. It could eject some small bodies. It could also redirect others inward. Removing it did not create one obvious universal change in impact risk. What changed beyond argument was the entire dynamical map. The solar system required a new census. A student looks again at the dashed giant planet trajectories. Will they just keep going forever? Not in mathematically perfect straight lines forever. The galaxy still exists. Passing stars exist. Galactic gravity exists. Over very long times, their paths will change. But there's still planets? Elena smiles. Of course. A planet does not stop being a planet because it no longer belongs to the star where it formed. Jupiter did not die. Saturn did not die. Uranus and Neptune did not die. They became free floating worlds. Future stars may pass near them. Perhaps one will someday enter another planetary system and be deflected again. Perhaps not. Their story is now galactic rather than solar. The answer seems to comfort several children. One has been staring at the black hole symbol. She finally raises her hand. Did it get bright when it came close? A little, perhaps, but not like the pictures people imagined. Elena explains accretion again. A stellar mass black hole in a bright X-ray binary can shine intensely because a companion supplies gas. A quasar can blaze because a supermassive black hole is being fed enormous quantities of material. Their visitor was isolated. The solar wind is extraordinarily thin. As the black hole moved inward, some plasma could be gravitationally focused and heated, producing detectable emission depending on complicated accretion physics. But there was no reason to expect a miniature quasar beside Jupiter. We mostly knew it by gravity, Elena says. Other things moved. Another child asks, was the sun thrown out of the galaxy? No. The sun did receive a substantial velocity change. Its future path through the Milky Way differed from what it would have been. But the sun already moves around the galaxy at a speed of hundreds of kilometers per second. Our encounter changed its galactic orbit without automatically providing enough speed to escape the Milky Way. Millions of years from now, the surviving solar system will occupy a somewhat different galactic trajectory because of an event that lasted one human lifetime. The children like this idea. A change that is invisible from the playground but lasts millions of years. Then one child asks the question Elena remembers most clearly. Do you hate the black hole? She pauses. Can you hate an orbit? The black hole did not choose the sun. It did not choose Jupiter. It did not know Earth existed. It followed gravity. The word disaster describes what happened to human beings. It does not describe an intention in nature. No, Elena says. I was afraid of it. I never hated it. Even though it took Jupiter, it didn't take Jupiter on purpose. The student looks at the dashed line for the giant planet, then asks, was it beautiful? Elena looks toward the old astrometric image on the wall, the star that shifted, Faraday's distorted star field, the mathematical curves, the impossible precision with which generations reconstructed an invisible object's motion. The answer is yes. That answer once felt almost disloyal. It no longer does. The lensing was beautiful, she says. The physics was beautiful. Watching planets leave was terrible. Both. The child accepts that immediately. A thing does not have to fit into one category. The universe certainly does not. Before the children leave, Elena asks them to look once more at the dashed trajectories. Those are not memorial decorations, she tells them. They are predictions. The lines will keep being updated as the giant planets recede, as passing stars perturb them, and as the galaxy bends their paths over enormous times. A lost planet was not erased. A changed solar system was not a dead solar system. And survival did not mean restoring the arrangement that existed before. It meant learning how to live in the arrangement that remained. After the class, Matteo helps Elena into a car. The drive home takes them past a public observatory. The dome is open. A line of children waits for a telescope. Elena asks the driver to stop. Matteo looks at her. You just spent 2 hours with children. These ones have a telescope. He cannot argue with that. The staff recognize her, but she asks them not to announce anything. She joins the line. The telescope is pointed at Saturn, or rather, at where Saturn is now. The ringed planet is far fainter than it would have been in the old solar system, already receding along its escape trajectory. It takes a large instrument to show much. When Elena reaches the eyepiece, the image is small, pale. The rings are still there. For a moment, she is 34 again. The black hole has not been discovered. Saturn is a planet returning predictably every orbit. Jupiter belongs to the sun. Neptune is blue and distant. The future contains no date marked perihelion. Then the memory passes. She looks again. This Saturn is real. The old one is memory. There is no rule that reality must preserve the arrangement in which you first learned it. Astronomy has always known that. Stars are born. Stars move. Stars die. Galaxies merge. Orbits change. The solar system only looked permanent because human lives were short compared with its usual timescales. The black hole compressed celestial change into one lifetime. Elena steps away from the eyepiece. A child behind her asks his father what Saturn used to look like when it was closer. The father opens an old image. The child compares screen and telescope, history and sky. Elena leaves without introducing herself. That evening she sits outside. Earth is moving toward the colder, more distant portion of its new orbit. The air is cool. The moon rises. Its timing is not exactly what an almanac from Elena's youth would have predicted, but its face is familiar. That continuity means more to her than she expected. She looks toward the region where the black hole is receding. There is nothing to see. That feels appropriate. The object entered human history invisibly. It leaves the same way. What remains visible is everything it changed. The altered planets, the new seasons, the infrastructure built to survive, the people born afterward, the empty places in old planetary diagrams. The black hole itself will continue through the Milky Way without carrying a memory of any of it. And now we can leave Elena there, beneath a solar system that survived by becoming a different solar system, and return to the one above us tonight. In the real sky, there is no known 10 solar mass black hole 600 AU away and heading toward Jupiter's orbit. The black holes astronomers actually know in our galactic neighborhood are vastly farther away. Gaia BH1, one of the nearest known black holes, is roughly 1,500 light-years from us and orbits an ordinary star. Gaia BH3, an unusually massive dormant stellar origin black hole of about 33 solar masses, is roughly 2,000 light-years away. Those are close by galactic standards. They are unimaginably far compared with the solar system. Astronomers have also used microlensing to identify isolated dark compact objects, demonstrating that a black hole without a bright companion really can reveal itself through gravity alone. That real science is what makes tonight's scenario possible to explore without pretending the threat itself is real. The Milky Way may contain enormous numbers of stellar remnants. Most are separated from us by distances so large that their gravity is irrelevant to the solar system. A random close passage by a stellar mass black hole is therefore not something you need to prepare for. There is no current astronomical evidence of one approaching the planets. And there is another reassuring fact hidden inside our story. The solar system has existed for about 4.5 billion years. During that time, stars have passed at varying distances. The sun has orbited the galaxy many times. The solar system has survived gravitational encounters, galactic tides, supernovae in the broader stellar neighborhood, and the slow redistribution of comets. Close stellar encounters do happen on astronomical timescales. An encounter as extreme as the one we imagined is different precisely because it is rare. Tonight's black hole was chosen not because it is likely, It was chosen because it lets us expose how a planetary system really works. There are no rails under the planets. No invisible grooves holding Jupiter at 5 AU. No permanent circles painted around the sun. There is motion. There is gravity. There are initial conditions. A planet remains a planet of the sun because its position and velocity keep it gravitationally bound. The stability looks solid because the equations repeat the pattern for enormous stretches of time. Change the gravitational environment strongly enough, and the architecture can be rewritten. That is true without black holes. A passing star can disturb a planetary system. A migrating giant planet can scatter smaller worlds. Young planetary systems can eject planets during formation. We observe planets on eccentric orbits around other stars. We infer worlds that probably migrated far from where they formed. The calm arrangement we inherited is one possible outcome among many. This is one reason astronomers study exoplanets so intensely. They show us solar systems that made different dynamical choices, if we can use that word for processes without intention. Hot Jupiters orbit close to their stars. Giant planets follow elongated paths. Multiple planets sit in resonances. Other worlds have likely been expelled entirely. Our black hole encounter takes mechanisms that ordinarily unfold in distant systems or ancient history and makes them happen where we can watch. The result is frightening because it removes a background assumption. We live as though the astronomical part of our environment is fixed. Weather changes. Politics changes. People age. But the year is the year. The sun rises where expected. Jupiter returns. Saturn returns. Neptune stays in the outer dark. The stars move so slowly that constellations survive many human generations. A black hole entering the solar system would remind us that celestial stability is physical, not promised. And yet this should not make the real night sky feel fragile. Physical stability can be extraordinarily strong. Earth's orbit does not need a promise. It has momentum and the sun's gravity. The moon does not need intention to return each month. Its orbit follows physics. Jupiter is not held in place by luck renewed every morning. It is part of a dynamical system that has persisted across most of the history of the solar system. The fact that a sufficiently massive close passerby could disrupt that system does not mean one is on the way. A bridge can be destroyed by an extraordinary impact and still be a stable bridge tonight. A coastline can be changed by a rare event and still be quiet now. Possibility is not probability. That distinction matters in almost every what-if question. We deliberately take an unlikely condition and ask physics to continue from there. The value is not predicting what will happen tomorrow. It is discovering which assumptions we're doing hidden work today. Tonight, one hidden assumption was that the sun is by far the dominant nearby mass. Usually it is. Jupiter contains more mass than all the other planets combined, yet the sun still outweighs Jupiter by roughly 1,000 to 1. That enormous dominance is why the planetary system behaves so cleanly. Our fictional black hole reverses the hierarchy. Suddenly, an object 10 times more massive than the sun enters the planetary region. The sun stops looking like the unquestioned center and becomes the lighter member of an encounter. That single change explains most of the catastrophe. Another hidden assumption was that seeing danger means seeing light. Black holes challenge that intuition. An isolated dark mass may be detected through what it does rather than what it emits. A background star brightens. Its apparent position shifts. A planet deviates. A spacecraft trajectory changes. Gravity becomes the messenger. And another hidden assumption was that survival means preventing the event. Humanity could not prevent our fictional passage. That did not make 57 years useless. Those years allowed measurement, preparation, infrastructure, food systems, energy systems, spacecraft, archives, training. The exact number of survivors in such a fictional future would depend on thousands of choices we cannot responsibly predict. But warning converts an unknowable catastrophe into a problem with decisions inside it. That may be the most human part of the story. Elena never stopped the black hole. She helped turn uncertainty into information. Matteo never moved Earth. He helped keep energy systems working on the Earth that emerged. Farmers did not restore the old orbit. They learned new seasons. Children did not bring Jupiter home. They learned what the dashed line on the classroom model meant. Humanity's power was smaller than the cosmic event. It was not zero. Now imagine the real solar system for one final moment. The Sun at the center. Mercury moving quickly through its small orbit. Venus beneath its bright clouds. Earth where it has been all evening, carrying oceans, cities, forests, sleeping animals, and everyone you know. Mars farther out. Jupiter still there. Saturn still there. Uranus and Neptune still moving slowly through the cold outer system. Beyond them, distant icy populations fading into darkness. And beyond that, interstellar space. There are black holes somewhere in the galaxy. There are neutron stars. There are wandering planets. There are stars moving on paths that will carry them closer to or farther from the Sun over immense timescales. The galaxy is not empty. It is simply vast. Vastness is part of our protection. You do not need an astronomer standing watch beside your bed. You do not need to imagine an invisible mass crossing Neptune tonight. There is no known incoming black hole rewriting the planetary system. The dramatic clock we followed existed only because we placed it there for the thought experiment. So let it disappear now. Let the 57-year countdown vanish. Let Neptune return to the orbit you already know. Let Jupiter come back from its fictional interstellar path. Let Saturn's rings remain where they are. Let Elena's altered calendar fold away. The actual Earth continues around the actual Sun. Not because the universe guarantees nothing can ever change. Because, at this moment, the conditions that make this orbit stable are still here. The Sun's mass, Earth's velocity, the enormous distances to other stellar systems, the quiet repetition of gravity doing exactly what it did yesterday. If your thoughts are still moving through numbers, let them slow. 10 solar masses, 600 AU, 5 AU, 57 years, 30 kilometers of event horizon. They were useful numbers for building an impossible night. They do not need to follow you into sleep. What remains can be simpler. A planet moving through darkness, a star holding it in orbit, a moon traveling with it. No sensation of the enormous speed because everything nearby shares the motion. No need to feel the gravity that curves Earth's path because falling around the Sun is what the planet has always done. Somewhere, real astronomers are measuring stars with impossible precision by historical standards. They are watching planets around other suns. They are finding dark companions through tiny wobbles. They are measuring the bending of light. Not because a black hole is known to be coming here. Because understanding the universe is what astronomy is for. Tonight we borrowed those tools and pointed them at something that is not there. We watched a star brighten. We followed the invisible mass inward. We saw the outer planets leave. We let Earth survive on a changed path. And then we put the solar system back exactly where we found it. There is nothing more you need to calculate. Nothing more you need to defend. The black hole is gone from the story. The real night remains. Let your body settle a little more heavily into whatever is holding you. Gravity here is ordinary, local, familiar. The same Earth beneath you that was here before we began. Let Jupiter keep its orbit without your attention. Let Neptune continue slowly through the outer dark. Let every distant black hole remain distant. There will be other enormous questions another night. For now, the solar system can continue without being watched. And so can you. Good night.